looking at 7.1, and we are jumping into exponential functions, and today we're focusing on growth and decay. So, definition of exponential function. Exponential function f with the base of a is denoted by this. So we have f of x equals a to the power of x. And that's the new thing, is that now we are allowed to have a variable as the exponent. That's what makes it an exponential function. So a has to be a number greater than 0. Your base cannot be 0. Your base cannot be a negative. So a is a number greater than 0, but a can't be 1, because 1 to any power is just going to be 1. X can be any real number. So again, having that variable exponent is what makes it an exponential function. So we're going to definitely be using our calculators for this. Use a calculator to evaluate the function, the value of x. So we are doing f of negative 3.1. That's what it would look like in function notation. And put it in 2 to the negative 3.1. Now here's one thing that I know. If you are thinking about this, wouldn't a negative exponent take this and flip it to the bottom? So I'm definitely going to get a decimal or a fraction. And so we're just taking this and we're expecting it to be put in a calculator. And so I am typing in 2 to the power of negative 3.1. Hit enter, and I get the decimal. And so I'm going to round this to the nearest hundredth, and it'll be 0.12. Now, if I needed this as a fraction, which I don't know if that will really work, you can go into your math key, and you can go over and just say, hey, I want this in as a fraction. I don't think it's going to give it to me because of the 0.1. But just to throw this out there, if it was 2 to just the negative third, I'm going to get that 1.125. And as a fraction, it'd be 1/8, because 2 to the third is 8, and we would just move it to the bottom. Okay, so just throwing that in there. Next one, let's evaluate f of pi. So I'll use my pi key, and it's going to be 2 to the negative pi. So what is f of pi? So take 2 to the power of pi. Your pi key in this calculator is second and then the power button. There's your pi key. Oh, it needs to be negative pi, right? There we go. And I get 0.1133, so I'm just going to go with 0.11. All right, go ahead and do the last one here. F of 3/2 is going to equal 0.6 to the power of 3/2. So I'm rewriting my answer in function notation. So 0.6 to the power of, whoops. And I'm going to go in with my fraction. I can do that, and it's going to be 3/2. And it gives me nearest hundredth to be 0.46. Okay, so all of these were exponential functions because they all had a variable exponent. Okay, now let's look at these graphs of two different exponents. So everything's on here for us. First things first, we have f of x is 2 to the 4th and g of x is 4 to the x. So look at the graph. They both look like they're in the same spot. One's a little bit layered here. And then we start seeing this 2 to the x starts taking off, but 4 to the x takes off and starts growing faster. Okay, so there's your function f of x, there's your function g of x. So what's happening? We have the function, the values of x. This one is for f of x, and this one is for g of x. And so we're putting in the same x values, and you can see we have 1/8 and 1/64, and 1/4 and 1/16. Now I want to remind you, this is an asymptote at y equals 0. The graph's going to get really close to it, but it will never be negative. Anything to base of 2 to a power is always going to be a positive number. So even if the power is a negative 100, it's just going to make it that fraction of 1/2 to the 100th. And if I make it a positive number like 2 to the 3rd, I get 8. So I'm never going to get a negative number out. So it's going to get really close to 0. This one is going to grow faster because the base is 4. So you can see that all my numbers are 4 times. This is 4 times big, twice as big. This is the same, and then the denominator starts doubling here. All right, both graphs are increasing. The graph of 4 to the x is increasing more rapidly than 2 to the x. Okay, so if we look at another one, same function, 2 to the x is shown, and the domain is all real numbers. Okay, that's important. We can put anything in for x, positives, negatives, fractions, decimals, anything can go in for x, but the range is greater than 0. So that is your, remember that set builder notation, y such that y is greater than 0. Or if we did domain as interval notation, negative to positive infinity, and the range would be 0 to infinity, not including 0. So again, we're putting in negative values and we're getting close to 0. If I'd put in -4, I'd get closer to 0. So an exponential function is going to start taking off and growing very quickly. It almost looks like it's going to turn into a line, but it will always have a little bit of a tilt to it. X is increasing, but y is really increasing. So the x values decrease, the graph gets closer and closer to the x-axis, or where y equals 0. The function never reaches the x-axis because 2 to the x can't be 0. It also can't be a negative. So that's why the x-axis is considered an asymptote. And we know that an asymptote is a line that a graph approaches but will never cross. So if we put in our calculator 2 to the negative 25th, I'm going to get this. This is scientific notation, 2.98 times 10 to the negative 8. That means we moved this decimal 8 places to the left, so we'd have 0.70 as the number 2. Do you get the idea that it's just going to keep getting closer to 0? Okay, so now consider this function. We have 2 to the negative x. Let's find these values. So we're just going to plug it in. 2 to the negative 2. Wasn't that going to be 2 to the second? So pay attention. You have a -2, but it's a negative x. So this would be 4. You could put it in your calculator. This would be 2 to the -1, which is 2 to the first, which is 2. What's anything to the power of 0? What's -1?
-1 to the first. I'm so stupid.
Okay, do you catch that the power is up here?
No, I'm just being stupid.
Okay. Anything to the power of 0, this is -0, which is 0. Anything to the power of 0 will just be +1, not 0, but 1. Now what happens here? A negative exponent flips it, so won't that be 1/2 or 1/2, 0.5? And this would be 2 to the negative second, so we flip it to 1/2 to the second, which is 1/4 or 0.25. All right, could I have used my calculator to do that? Absolutely. We should be comfortable putting that in the calculator. That would have been 2 to the power of -2, and there's that 0.25. Okay, so go ahead, take a second and graph this. But you have to wrap your head around how this is, changing compared to what we did before. Now, what are you noticing about this graph that's different than the other ones that we already looked at? No one sees anything different? Now, hopefully you can actually get your points hit, which I didn't do a great job of. Well, this graph is dropping, where the other one we looked at was increasing, and the two on the front were increasing. As x was increasing, y was really increasing. So as x increased, y just started jumping up. But now as x is increasing, y is decreasing. So this would be considered, a different looking graph, and it's because of that negative exponent. Okay, so compare it to this one. Let's do 2 to the x. So this would be 2 to the -2, which would be, remember, it's not a negative number. It's going to be 1/2 squared, so 1/4. So we're inverting these. 2 to the -1 is the same as 1/2 to the first. 2 to the 0 is 1. 2 to the first is 2. And 2 to the second is 4. So if you take a minute and you graph this one, here we're starting close to 0, not at 0, but close to 0. And then my graph is increasing. Now, if I needed a more accurate graph, I could keep going with points of 3 and 4, but they're going to go off my graph. And I could keep going with -3, -4. But remember, it's not going to cross the line. It's going to run along this x-axis, which is your asymptote. All right, so the big difference here is this now both x and y are increasing. We're here as x is increasing, y is decreasing. Okay, so let's talk about some terms here. Exponential growth is when it's increasing, 2 to the x. So we can see that right here in this graph. Our graph is growing. Let's explore to the negative 1 or to the negative x, which is exponential decay, as in we're losing something. Y equals 2 to the negative x can be written as a power to power exponent. So if you look at this, it's 2 to the negative 1 times x. So 2 to the negative 1, couldn't I rewrite that as 1 over 2 to the x? Well, it says rewrite 2 to the negative 1 on function above. So you could write it as 1 over 2. So in general, this formula could be y equals 1 over 2 to the x. Or 1 over 2 all to the power of x. And anytime you have something less than 1 but greater than 0, it's decaying. Okay? So let's explore that a little bit more. So if your base is a number greater than 1, your graph is going to be growing. If your base is between 0 and 1, can't be 1, it can't be 0, you're going to be decaying and your graph is going to be dropping. Okay, so here are sort of the rules here. The base of an exponential function indicates whether the function is growth or decay. So it's f of x equals ab to the x. A is always a constant, just like before, okay? But the base is b. That's what we're talking about. So if your base is between 0 and 1, it's going to show decay. So if you think about it, 100% of something is going to give us back what we have. But if we have 105%, we'll get it back plus more, right? But if we're losing, like if we only have 90% of what we're starting with, we're losing it. And that's the idea. And I'm talking about percent because 0 is like 0% and 1 is like 100%. So between 0 and 1 or less than 100%, it's decay. But if your base is greater than 1, it's showing growth. X is always going to be an exponent. So here's another example. F of x equals 1.2 to the power of x. A is 1. So if you really think about it, it's like this. The a value is 1, the base is 1.2, and b is greater than 1. So if we graphed it, this shows exponential growth. And I'm going to throw this in here. This 1.2 is the same as saying 120%, because this is going to help us later with word problems. 120% means you had 100% and you added on 20%. And so if we said something was growing by 20%, we would consider 1.2 our multiplier. So 1.2 comes from 120%, which is 100% plus 20. That's how I know it's growth. I had 100%, I add on 20%. Okay, now look at this one. A is 10, that's that front number. Our base is 0.6, which is between 0 and 1, so we're talking about exponential decay. Now, 0.6 is a little bit different. 0.6 is 60%, but that's what you have. So if you're talking about decay, someone might be saying this is decaying by 40%. So why am I bringing that up? Well, you always start with 100%, and if I take away 40%, what's left? 60%. So growth is 100% plus, but decay comes from 100% minus. So something must have been decaying by 40% because we have 0.6 left, or 60% left. Okay, so look at this. Is number 1A growth or decay? This one is growth because A is 1, B is 1.5. So this is growth. If you weren't sure, you could graph it. You would see that upward trend. Okay, 30 is the A value, and the B value, what's the base, is 0.8. So this is growth or decay? This is decay. So I have 80% left of something. That means we've lost 20%. Okay, example, try this, A. Go ahead, take a second, determine if it's growth or decay. Three-fourths is the same as writing it as what? 0.75? So either way you cut it, this is less than 1, between 0 and 1. So A is 10, B is 0.75, so this is decay. And what about B? A is 100, B is 1.05, so this is growth. Remember, 1.05 is going to be 100% plus 5%.